Most automatic transmissions use epicyclic or planetary gears. They are constantly in mesh with each other. A basic planetary gear set has a sun gear, which meshes with planet gears, also called planet pinions. The planet pinions, in sets of 3 or more, rotate on bearings, on hardened steel pins, on a planet carrier, which spaces the pinions equally around the sun gear. It also locates them so they can mesh with an internally toothed ring gear. This means the planet pinions are always in mesh with the sun gear and the ring gear. In operation, their motion is described as either walking or as idling. Walking means that if either the sun gear or the ring gear is held stationary, the alternative driving member rotates the planet gears on their pins. This turns the planet carrier in the same direction as the driving member. Planet gears always turn in the same direction on their pins as planet carrier rotation. While they walk around a stationary sun gear, they always turn in the opposite direction on their pins while walking inside a stationary ring gear. Idling refers to the rotation of the planet gears on their pins whenever the planet carrier is stationary. Torque is transmitted from the sun gear to the ring gear or from the ring gear to the sun gear via the planet gears and the stationary carrier. In both cases, the driven member is turned in the opposite direction to the driving member. To provide the ratios available from the gear set, one or more of the components must be held or released. This is normally done by hydraulic servos, operated by transmission fluid under pressure, acting on lined bands or clutches, or by one-way clutches. They allow turning in one direction, but act as a lock-up or reaction member in the opposite direction. In practice, a combination of these is normally used. A simple planetary gear set can illustrate how to control individual members to produce a particular output or neutral. This planet carrier is attached to the output shaft. The sun gear is attached to the input shaft from the turbine. The ring gear is not held. When the input shaft rotates the sun gear, the planet gears idle on their stationary carrier pins and turn the ring gear in the opposite direction to engine rotation. This free rotation of the gears provides neutral. No drive is transmitted to the output. For low gear, a brake band anchored to the transmission case is placed around the ring gear. Applying this holds the ring gear stationary. Now, when the sun gear rotates, the planet gears can no longer idle. They must walk around the inside of the stationary ring gear. The planet carrier must move with them in the same direction as engine rotation, but at a slower speed and with an increase in torque. A direct drive or top gear condition with a 1-to-1 ratio is obtained by locking together any two members of the gear set. A multi-plate clutch can be used for this purpose. The outer drum and outer plates are attached to the ring gear. The inner plates and inner drum are attached to the planet carrier. When fluid under pressure is directed onto the clutch piston, the clutch plates are locked together. This locks the planet carrier to the ring gear. Now, when the sun gear is rotated, the planet gears can neither idle nor walk. The whole gear set turns as one unit to give a direct drive. For reverse, the ring gear is attached to the output shaft. and the planet carrier is held stationary by a brake band. Rotating the sun gear causes the planet gears to idle on their stationary pins. This turns the ring gear and its output shaft in the opposite direction to engine rotation. The simple gear set illustrates basic principles, but it can't obtain all the ratios required. In practice, compound planetary gear sets are used. The Ravigno gear set has two simple gear sets with only one ring gear. All gears are always in mesh, just as in a simple gear set. A primary sun gear meshes with short primary pinions. A secondary sun gear meshes with long secondary pinions. Both sets of planet pinions are mounted in a common planet carrier, and they mesh in pairs. The outer secondary pinions mesh with the ring gear, which is attached to the output shaft. A Simpson gear set has two simple gear sets connected by a long sun gear common to both gear sets. The sun gear is free to rotate on the output shaft. It is constantly meshed with the planet pinions of both sets. They in turn mesh with their individual ring gears. Both sets are also connected by each having a part spline to the output shaft. The ring gear of the rear set and the planet carrier of the front set. The input shaft is separate from the gear set. The drive is transmitted through one or more clutches, depending on the gear and range engaged. Two bands and a one-way clutch are also used to control the gear set components. All bands are externally contracting types and have a thin layer of plain or grooved friction material bonded onto a spring steel or cast steel backing. One end of the band rests against a stop or strut in the transmission case. The other end accommodates a pushrod or linkage from a hydraulically operated servo, which contracts the band onto the drum. The simplest servo consists of a cylinder containing a piston return spring, and a pushrod. Fluid leakage past the piston is normally prevented by neoprene-type seals. Fluid under pressure is directed onto the piston in the closed cylinder, moving it to apply the band. When this fluid is dumped or exhausted from the supply line, the spring returns the piston, and the flexible band springs back to its released position. In a pressure release type servo, the band is applied in the normal way by fluid pressure acting on the piston head. However, this fluid is not dumped to accomplish band release. Release is obtained by supplying fluid at the same pressure to the opposite side of the piston. As soon as pressure is equal on both sides of the piston is moved to the release position by the force of the return spring acting on the release side. The band speed of application or release is controlled by the rate at which fluid on the release side enters or leaves the servo. When admitting release fluid is unrestricted, the band is released quickly. When dumping it is unrestricted, a snap band application occurs. This is because fluid under pressure is already acting on the servo piston. Pressure release servos can also have pistons with unequal areas. In this case, the release side has a larger surface area than the apply side. The band is brought into operation by directing fluid onto the reduced area that surrounds the hollow portion, accommodating the return spring. When fluid at the same pressure is directed to the release side, the differential area results in a higher release force. The band can be released even while apply fluid continues to exert force on the piston. The fluid directed to the release side can be directed at the same time to a clutch piston to bring the next component into operation. Multiple disc clutches can be used to hold members to the case instead of using bands, but in most transmissions, they couple planetary gear members and shafts together. A servo-operated band can only hold a member stationary, but multiple disc clutches can hold or drive individual members. They have a set of driving plates and a set of driven plates, collectively called a clutch pack. Both sets may be spring steel, but one has friction material bonded onto both faces. And since they operate in the transmission fluid, they are called wet clutches. The friction material may be plain or grooved. Grooving allows for fluid to escape from between the plates when the clutch engages. The steel plates may be dished or waved, with alternate high and low segments. This design promotes smooth engagement. The size and number of plates in a clutch pack depends on the maximum torque it is required to transmit. 3 to 5 plates of each type are commonly used. The plates are pressed together for engagement by a hydraulically operated piston. It moves in a short cylinder in a clutch drum or in a cylinder machined in the casing. Release can be effected by one large coil spring or by a pack containing many small springs. When a diaphragm spring is used, it gives extra leverage to increase the apply force as well as providing the release force. The outer circumference of the diaphragm spring rests against a step in the clutch drum. The piston pushes against the inner circumference of the spring to apply the clutch. The force exerted on the clutch pack is multiplied by leverage from the diaphragm as it pivots against the pressure plate. In the released position, the plates must retain a set clearance. This allows them to separate from one another and avoid excessive or premature wear. Premature wear can also be caused by partial application of a clutch at high speed. This can occur if fluid is trapped in the clutch cylinder after release. Trapped fluid accumulates at the outer portion of the cylinder. At high speed and under the action of centrifugal force, this can produce enough pressure to effect partial application. This can be prevented by a pressure relief valve in the piston. It is normally a flat reed or ball check type, which is easily closed by the apply fluid. On release, the valve is unseated by the rotation of the assembly, letting fluid escape. One-way clutches are used in the gear train to allow rotary motion in one direction only. They simplify the hydraulic and mechanical control of the members. The hydraulic control system requires a continuous supply of fluid under pressure, normally provided by a fixed displacement pump. It is driven by the torque converter when the engine is running. The pump driving member is engaged by tangs on the converter spout, or machined flats, or by slots. Pump output always exceeds normal operating demands, so pressures are controlled by regulating valves. Excess fluid returns to the pump inlet or is dumped into the oil pan, where it can reach the pump intake strainer. Crescent-type pumps are commonly used in automatic transmissions.